Hello, my name is Aslı Kanber. I'm a second-year computer science student at Bilkent University. Today, I will be presenting you my Physics 101 project, which is computing the terminal velocity constant using 4 different environments. And I used salt and water to make these 4 environments, and I observed the change in terminal velocities and terminal velocity constants. First of all, let me explain what terminal velocity is. It is the maximum speed that an object can reach in an environment. So, when an object is falling, it encounters a downwards gravitational force, and opposing to that force, there's a drag force generated by the particles in the environment. Drag force is proportionate to the velocity when the object is small and it's moving at small speeds, such as if it's moving in a viscous fluid, or the object is small as dust. For bigger objects, the drag force is proportionate to the velocity squared. So for like a baseball or plane or a skydiver, it is proportionate to v squared. So when the velocity of the object increases, its corresponding drag force increases, and after some time, its drag force and gravitational force becomes equal, and by Newton's second law, its acceleration also becomes zero, and the object moves at a constant speed, and that speed is called terminal speed. For this experiment, we will need tap water, small metal ball around 3 mm of diameter, measuring cylinder or a long glass tube, a ruler, a camera can be of the phones, scientific calculator, rubber band, scale, magnet, micrometer, beaker, salt, plate, spoon, and a motion capture software. First of all, I measured the mass of the empty glass tube in order to find the mass of the liquid inside the glass tube later on. Then, measured the volume of the water with beaker and filled the glass tube with it. I dropped the ball and recorded the video. Then, I measured 100.78 grams of salt. Then I added the salt to the water. Then I mixed it until it fully dissolved. Then I did the experiment again when I dropped the ball. Then I measured another 100.2 grams of salt and added it to the mixture. I mixed it until it fully dissolved. Then I measured the mass of the salty water. I did this for the other steps as well, but I forgot to take a picture of it. Then I did the experiment again. First, I measured 100.03 grams of salt. Then I added it to the liquid. Then I mixed it in another bowl because the volume was bigger than of the volume of the tube. Then I transferred the liquid into the tube. Then I did the experiment last time. After I've recorded the videos, I sent the videos into a motion capture software and extracted the displacement, time, velocity, acceleration data from the software. First, I transferred the data from the software and filled the tables: time versus displacement, time versus average velocity of the last 4 data points, and time versus velocity. Then I plotted the graph of time versus velocity and time versus acceleration. Using the formula given above, I calculated the density of each environment. Then I found the average of the average velocities that we found earlier on and calculated the terminal velocity in each environment. Then I filled the table using density and terminal velocity. Using the given formula, I calculated the terminal velocity constant for all environments and found the error percentages. These errors could be a result of incorrect marking while using motion capture software and the limited ability of the camera to capture 60 FPS per second, and we cannot get a clear image of the object at each time interval. In conclusion, the theoretical value for terminal velocity constant is 0.47 and is computed by using various variables such as viscosity of the fluid, density of the fluid, the shape of the object, and Reynolds number. So it's a very difficult computation to make, and is 0.47 for spherical objects. In our observations, our terminal velocity constants were actually pretty similar to the theoretical value. So I conclude that the density of the environment does not change the terminal velocity constant for a spherical object, and it is close to 0.47. Thank you for listening.